Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we're going to be doing the exercise set, the self-test, number 3, Form B, and the usual admonition: please don't watch this tape until you've tried the problems in both Form A and Form B. Get as much experience as possible before you watch each of the solution set tapes. Today's exercise set is designed primarily to make sure you understand the concepts of multiplication, and we'll go through this in more detail, problem by problem. Let's go over to the board and see what's happening today. The first problem asks us to list the first 4 multiples of 16. And in terms of what this means, all we're saying is if you were counting by 16s, what's the 4th number you'd come to? In other words, at 16 cents each, what would 1 object cost, 2 objects, 3 objects, 4 objects? And we can, of course, do that just by simple arithmetic. You see, the first multiple of 16, which, by the way, we will call 16 times 1 in the language of multiplication, is 16. The second multiple would be 16 plus 16, which we write as 16 times 2. And by the way, notice in this form that the adjective is the second number. You see, this is the second multiple of 16. See, it's the sum of 2 16s. Then if we add on 16 more, we get to 48. And if we add on 16 to 48, we get 64. And by the way, if you didn't want to do the problem that way, you could have written the problem as a vertical form multiplication problem. In other words, when you say, what's the 4th multiple of 16? It's 16 times 4. 4 times 6 is 24. Put down the 4 and carry the 2. 4 times 1 is 4, and 2 is 6. And now we have the same answer. Next problem is exactly the same as Part A, only now it asks us to list the first 4 multiples of 24. We're going to do the same thing we did in Part A, except now we're going to count by 24s instead of by 16s. So you see, list the first 4 multiples of 24. 24 times 1 is 24. Then the sum of 2 24s, that's 24 plus 24, that would be 48. The sum of 3 24s would be to add 24 onto 48. That would give you 72. And again, if you wanted to do that a shorter way, it's what? The third multiple of 24. The noun goes on top, the adjective on the bottom here. 3 times 4 is 12. Put down the 2 and carry the 1. 3 times 2 is 6, and 1 is 7. You see there's the same 72. And now for the 4th multiple, we add 24 to 72 and get 96. Part C of this problem is extremely important, not so much just for getting the right answer, but because it's going to play a vital role in the next module. And for this reason, I want you to get used to the wording of Part C, because you're going to hear it several times during the remainder of the course. See, Part C says, what is the smallest non-zero number that has 16 and 24 as factors? Now, the reason I say non-zero here is because 0 is a multiple of every number. See, 16 times 0 is 0. 24 times 0 is 0. So we want a number which isn't 0. And what this means in different language is if you were counting by both 16s and by 24s, what is the first number you'd come to? In other words, what is the least common multiple of both 16 and 24? And perhaps the easiest way to solve this problem, see, is to simply look at the answers to Part A and to Part B. You see, when we count by 16s, 16 is on the multiples of 16 list, but it's not on the multiples of 24 list. If you just look at this, I think it takes only a second or so to discover that 48 is the first number, which is a multiple of both 16 and 24. And that's all this problem is asking us to do. See, the most common mistake that people make is that they give me 8 as the answer. See, 8 is a factor, not a multiple of 16. See, 8 goes into 16, 8 goes into 24. We're looking for the smallest non-zero number that both 16 and 24 go into. You see, 48 is the least common multiple of 16 and 24. 8 is the greatest common factor of 16 and 24. They're different problems, but I just want you to understand that. I also want you to understand that if we weren't looking for the least common multiple, there is a very simple way to find a common multiple of any two numbers. Namely, 24 times 16 is 384. That computation is done on the side here in case you want it. But the interesting point is what? That 24 times 16 is both what? It's the 16th multiple of 24. That means that if you were counting by 24s, 384 would be the 16th number you'd come to. And it's also the 24th multiple of 16. That means if you were counting by 16s, 384 would be the 24th number you'd come to. But the interesting point is that without listing all of those, you do come to a common multiple of 16 and 24 much sooner, and that common multiple is 48. At any rate, that's enough for problem number 1. Let's go on now to problem number 2. And again, as I say, these problems aren't that exciting, but they are meant to cement down the details. You have to walk before you can run. Let's make sure we understand the vocabulary and how to use it. Part A in problem 2 says, how much is 82 times 6? Which is simply another way of saying what? What is the 6th multiple of 82? In other words, if you were counting by 82, what's the 6th number you'd come to? And let me show you an evolution of how we can do this. You see, perhaps the most primitive way is to say, okay, we'll start with 82, then we'll add on one more 82. 82 and 82 is 164. Then we'll add on one more 82. 82 and 164 is 246. So the sum of three 82s is 246. In other words, the third multiple of 82 is 246. We could keep on going this way. But a shorter version simply says what? Let's list vertically the 82 6 times and just add them up. You see, we have what? 2, 4, 6, 8, 10, 12. Put down the 2 and carry the 1. Then we have what? 8, 16, 24, 32, 40, 48, 49. So the answer would appear to be 492. And by the way, notice that even though this took a long time to write down, when we got through, do you notice the multiplication here? In effect, what we said was what? We have 6 2's here, and 2 times 6 is 12. Put down the 2 and carry the 1. Then we have what? 6 8's. That's 48 because we've learned our multiplication tables, and one more is 49. So rather than write all this, we simply go into an abbreviated notation. And what we write is what? 82 times 6, and we say what? 6 times 2 is 12, see? And 12 what? 1s times 1s are 1s. Then 6 times 8 is 48. 48 what? 48 tens. And you notice that that's the same answer we got by addition? We had 12 1s and 48 10s, but we could take 10 of our 1s and trade them in for one more 10, giving us 492 as the answer. And then the final step in our evolution is the very compact form that says what? 6 times 2 is 12. Put down the 2 and carry the 1. See, we trade in the 10 1s right away. Then we say 6 times 8 is 48, and the one that we carried is 49, and the answer is still 492. Now, Part B is designed to show you how the basic structure of multiplication is unaltered by annexing zeros. See, Part B says, how much is 82 times 60? Conceptually, if you're thinking about this the long way, this is a fairly difficult problem. You see, what this problem says is, look, if you're counting by 82s, what's the 60th number you come to? That's a lot different than say, what's the 6th number you're coming to, because it doesn't take too long to count out 6 multiples of 82. But 60 multiples of 8, the 60th multiple of 82, that is quite far along in our list. And the way we get around that, well, there are several ways to look at it. One way is to say, look, 60 is another way of saying 6 tens. So what you're really doing is taking what? 6 tens 82 times. In other words, 82 times 6 is still 492, but 492 tens, how do you multiply by 10? You tack on a 0, so the answer would be 4,920. Now, if you want to see this in a nonverbal form, just by using the properties of multiplication, notice that another way of writing 60 is as 6 times 10. And then, since multiplication has the associative property, we can reread this as if it was what? 82 times 6 multiplied by 10. You see, we can shift the parentheses over here. In part A, we found out that this was 492. Now how do we multiply by 10? We just annex a 0. And there's the same answer, 4,920. What's the more traditional way of doing this? The more traditional way is what? We put the noun on top and the adjective on the bottom, and we write 82 times 60. And what's the rule? Each digit in the downstairs number multiplies each digit in the upstairs number. Each digit on the bottom number multiplies each digit on the top number, and you say what? 0 times 2 is 0, 0 times 8 is 0, 6 times 2 is 12, put down the 2 and carry the 1. Okay, 6 times 8 is 48, and 1 is 49. Now you add this up, and you get 4,920. And again, notice that the reason for putting in these zeros is that the 6 over here is modifying tens. So 82 times 610 isn't 492. It's 492 tens, and putting the 2, you see, under this second 0 puts the 2 into the tens place. And the shortcut way of doing this that a lot of people use is they simply push the digits out by 1. In other words, they write the 60 like this. And then they imagine there's a line over here. Simply multiply the 82 times 6, which was part A of this problem, then annex the 0, and you still have 4,920 as the answer. And finally, if you want to see this the last way we explained it in the lecture on the module, what you do is view the problem this way. See, you still get the zeros over here, but later you say what? 6 tens times 2 ones is 12 tens, so the 12 goes in the tens place. 6 times 8 is 48, but tens times tens are hundreds, so the 48 goes into the hundreds place. So altogether we have no ones, 12 tens, and 48 hundreds. And then we can take what? 10 of our tens and trade them in for one more hundred, and now we get 4,920. See, no matter how we do the problem, as long as we don't make a mistake, we get the same answer. And I'm going to keep emphasizing that to you during the course because I don't want you to memorize. I will show you many ways of doing the problems, and you may still think of ways that I haven't shown you. That doesn't mean that your way is wrong. While there's only one right answer, there are many, many right methods usually. At any rate, let's now go on to part C. Part C says, how much is 8,200 times 600? And again, the shortcut way of doing this is to ignore the number of zeros to begin with, multiply the non-zero digits, in other words, 82 times 6. But we already know that that's 492. Then what do? We count the total number of zeros, 1, 2, 3, 4, and then we annex them, 1, 2, 3, 4. Then we put in the commas, and the answer is now what? 4,920,000. That's it. Now again, if you want to see the structure of this in terms of how I explained it in the lecture, see, 8,200 is what? It's 82 in the hundreds place. And 600 is also 600. Let's use the nouns now. See, we write it as what? 8,200 times 600. And 82 times 6 is 492, and 100 times 100 is 100 hundreds. And how do you write that? You see 100, and now you want 100 hundreds. That means 2 more zeros, so you have 492 this many times, and that tells you what? To annex the 4 zeros. You see, you're still going to get the same answer this way. Now, part D is designed to do 2 things. It's designed to show us, first of all, how a more complicated problem can be a combination of 2 simpler problems, and also to show us how the distributive property works when we deal with multiplication. Part D asks us, what is the 66th multiple of 82? In other words, if we were counting by 82s, what is the 66th number we'd come to? The thing to notice is that 66 is the same as 60 plus 6. So, in a sense, this says what? If you have 60 82s and 6 more 82s, altogether you have 66 82s. And by the way, that's not just true for multiplication, that's true in general. I mean, if you wanted 66 apple pies, if you had 60 apple pies and 6 more apple pies, that's 66 apple pies. If you want 66 82s, it's 60 82s plus 6 more 82s. And in the language of the distributive property, what it says is when a number is multiplying the sum of two numbers, the outside number multiplies the first inside number, then the outside number multiplies the second inside number, then we add both of these results. In other words, it's what? 82 times 60, which, by the way, is what we did in Part B, plus 82 times 6, which is what we did in Part A. Now, in Part B, we saw that 82 times 60 was 4,920. In Part A, we saw that 82 times 6 was 492. So therefore, all we have to do is add these two answers. You see, 4,920 plus 492. See, 2, 9 and 2 are 11. Put down the 1 and carry the 1. 4 and 9 are 13 and 1 is 14. Put down the 4 and carry the 1. 4 and 1 are 5. So the answer is 5,412. And if you didn't want to do the problem this way, you could have done it the so-called faster way. You could have said, okay, we'll put the noun on the top, the adjective on the bottom, and suddenly 82 times 66 becomes what? 82 times 66. We say 6 times 2 is 12, put down the 2 and carry the 1. 6 times 8 is 48, and 1 is 49. Same thing we did in Part A. Now we do what? 6 times 2 is 12, put down the 2 and carry the 1. 6 times 8 is 48, and 1 is 49. By the way, hopefully I get the same 3 digits here that I got here because I multiplied by the same number. You may wonder, why did I do it both times? And the answer is, in case I made a careless mistake, the likelihood is I'm not going to make the same careless mistake twice. In other words, if these two answers came out differently, it would tell me that I made a mistake. And again, keep in mind what this is. This 6 is 6 ones. By putting the 2 over here, that puts a 0 here. That gives me the 60th multiple. You see the 492 and the 4,920 again? And now what do? Just add them up. In other words, this is simply a different language, a more mechanized language, a more compact language for doing the same problem that we did equivalently just a few minutes ago. Okay? Now, problem 3 is designed to show you a couple of things. One is, up until now, we've only been multiplying two numbers at a time. Now I want to show you several things. First of all, that when you have more than two numbers to multiply at a time, all you have to do is multiply them two at a time. That's by the associative property. And the second thing I want to show you is that sometimes if you develop a number sense, since multiplication is also commutative, you can change the order of the factors, and that might sometimes make the problem easier. You see, problem number 3 asks us to multiply or to find the product of 6 times 82 times 50. Now, one way of doing this problem is in the order of appearance. You see, we can first do what? Multiply the 6 by the 82. Well, we just did that in the previous problem. 82 times 6 is 492. By the way, for the purist, the purist says, wait a second, this is the adjective and this is the noun. The way you've written this is you want the sum of 82 sixes. Granted, that's the same as the sum of 6 82s, but didn't you tell me that the adjective has to go on the bottom? Well, that's okay if you want to do it that way. The key point is what? Every digit in the bottom number is still going to multiply every digit in the top number. You see, 2 times 6 is still 12, isn't it? And then 8 times 6 is 48, but I still have to indent because the 8 is in the tens place. You see that? It's 8 tens times 6 ones, which is 48 tens. And the answer is still going to be what? 492. Either way, now I multiply that by 50, and using the shortcut method I showed you before, I take the 492, I multiply that by 5. You see 5 times 2 is 10, put down the 0, carry the 1. 5 times 9 is 45, and 1 is 46. Put down the 6 and carry the 4. 5 times 4 is 20, and 4 is 24. Then I annex the 0, and the answer is 24,600. Now, there's nothing wrong with that. The only thing I wanted to point out is that since multiplication is commutative, I can change the order of the factors. You see, going back to this, my eye may have picked up the fact that I can do 60 times 50 in my head. You see, 6 times 5 is 30, annex the 0, that's 300. In other words, I could have said what? 6 times 50 is 300. Then I'll multiply the 82 by 300, and that's exactly what I do down here. See, 82 times 300, 82 times 3, 3 times 2 is 6, 3 times 8 is 24. You see, that's 246. Now I annex the 2 zeros, and there's my same answer, 24,600. Are you starting to get the feel of this okay? Now, the next thing I want to do is to again teach you some number sense and to show you how you can sometimes make a complicated problem somewhat more simple. And the way I'm going to do that is I'm going to give you the simpler problem first and then show you the complication that comes up. Technically speaking, I could have called this two separate problems. The reason I labeled it A and B is that A will be a device to help make B easier to visualize. See, all problem A, part A of problem 4 says is what is the product of 821 and 500. By the way, I should warn you about a very common mistake that students sometimes tend to make here. A lot of times in elementary school, we're taught to look for addition whenever we see the word and. And a lot of times, the student sees the word and over here, and they say, oh, I know, 821 and 500 is 1,321. See, but notice that the key word here is product. Whenever you see the word product, it's a multiplication problem. You see that? It's not an addition problem. Product is the answer to a multiplication problem. The and here is just a conjunction connecting the two numbers that we're going to multiply. In other words, what we're saying is, if 821 and 500 are the factors, what is the product? And how do you multiply 821 times 500? Again, in terms of what we said before, just multiply the 821 by the 5. You see 5 times 1 is 5, 5 times 2 is 10, put down the 0, carry the 1, 5 times 8 is 40, and 1 is 41. Then annex the 2 zeros, and that gives you 410,500. Pretty straightforward, easy problem, I think. Part B is a slightly trickier one. Part B says, how much is 421 times 499? And you say to me, well, what's so tricky about that? I'm just looking for the 499th multiple of 821. And can I find that? Sure. It's just 821 times 499. Now look at the amount of work that's involved over here. What do I say? I say 9 times 1 is 9. 9 times 2 is 18. Put down the 8 and carry the 1. 9 times 8 is 72, and 1 is 73. Then I go over here. 9 times 1 is 9. Notice this is just going to be a check because it's the same digit, the 9 that I'm multiplying. 9 times 2 is 18. Put down the 8 and carry the 1. 9 times 8 is 72, and 1 is 73. And notice the indentation here. Okay, that's holding the place of a 0. Now the 4 gets indented one more place. 4 times 1 is 4. 4 times 2 is 8. 4 times 8 is 32. Then I add all these numbers up, and I get 409,679. And you see what I've done here? This is the sum of 9 821s. This is 90 more, and this is 400 more. See, this is the sum of 499 821s. If I was counting by 821s, 409,679 would be the 499th number I came to. Well, that's okay. But you notice that if you do this, I call this the brute force technique. It doesn't show any sophistication. It doesn't give you a feeling for the correct answer. See, what I would prefer to have you do is to say, hey, 499, isn't that just 1 less than 500? See, what I'd like you to say is, look, in the previous problem, we found out that 500 821s is 410,500. And now, if I take away 1 821 from 500, that would give me what? And this is tricky over here. See, I had 500 821s. I take away one of the 821s. That gives me what? 499 821s. The part that I call tricky isn't that you're subtracting 1. It's that you're subtracting 1 821. See, what you're going to do is what? This is the sum of 500 821s. This is 1 821. If I subtract 1 821 from 500 821s, what's left is 409,679, which is the same answer as before. In other words, all we're saying is, if you wanted 499 of anything, and the things came in bundles of 500, just take a bundle of 500 and take one away. Now, of course, you say to me, well, by the time you got through explaining all of that, wouldn't it have been quicker for me to just multiply by the 499 and not have to listen to your long-winded explanation? That's possibly quite true. But what I really want you to see is something much more sophisticated. I really don't care which way you do Part B, but here's what I do care about. I want you to be able to look at a problem like 821 times 499 and say, look, here's where rounding off comes in. 821 is rounded off to the nearest hundred to be 800. And 499 to the nearest hundred is 500. And 800 times 500 is an easy problem to do, because 8 times 5 is 40. Then you have what? 1, 2, 3, 4. 1, 2, 3, 4 zeros. So 800 times 500 is a problem you can practically do in your head. And that answer is what? 400,000. Therefore, before you even start this problem, either A or B, you know that the answer you're looking for is very close to 400,000. And that can guard against making some very serious mistakes, as I try to show you in the next exercise. The next exercise says, how much is 809 times 504? People sometimes have trouble keeping track of zeros. I'm going to show you an easy way to do this. Before you even start this problem, you say, look, 809 times 504, whatever the right answer is, 809 is a little bit bigger than 800. And 504 is a little bit bigger than 500. And we just saw that 800 times 500 is what? 400,000. Therefore, whatever the correct answer to this problem is, it has to be somewhat more than 400,000. Knowing that, and by the way, that doesn't take that long to do, but knowing that, I now have parameters in my mind to know what to look for. Let me first of all do this problem the more traditional way and get the right, hopefully the right way. Then I'll do it a traditional wrong way and show you that not only is the answer wrong, but you should have known it was wrong. See, the usual way of doing this is what? Every digit in the bottom number is going to multiply every digit in the top number. Same as before. See, 4 times 9 is 36. Put down the 6 and carry the 3. 4 times 0 is 0, and 3 is 3. 4 times 8 is 32. Now to hold your place, you put in all these zeros. See, 0 times 9 is 0. 0 times 0 is 0. 0 times 8 is 0. Then you indent again. See, 5 times 9 is 45. Put down the 5, carry the 4. 5 times 0 is 0, and 4 is 4. 5 times 8 is 40. Sounds almost like a ritual. But you get used to it, and now you get what? Add this all up, and you get 407,736. Now, I don't have the answer sheet in front of me. Is it possible I made a careless mistake here? It sure is. But what do I know? I know if I did make a careless mistake, it can't be too far off, because what did I estimate the answer was? It was supposed to be what? A little more than 400,000. A little more than is kind of subjective. I don't know what that means exactly, but looking at this number, would you say that this qualifies as being a little more than 400,000? You see, compare this with the person who does this problem incorrectly. They multiply the 809 by the 4, get the same 32, 36 that we got our way. Then the person says, well, 0's nothing, I'm just going to disregard it. Then they multiply by the 5, just as we did. But now instead of putting this 5 under the 2, they put the 5 under the 3. You see, even though the 5 was in the hundreds place, by putting it under the 3, you've treated it as 10 5s, not 100 5s. See, it's 50, not 500. Well, let me show you, after you do the problem this way, if you have any number sense at all, why you have to know this is the wrong answer. We just figured out before we started this problem that the correct answer has to be a little bit more than 400,000. Now, no matter what the right answer is, 43,686 is not a little bit more than 400,000. It's way less than 400,000. So this must be the wrong answer. Okay? I want to give you some more experience with using the distributive property and grouping symbols. So let me give you some more problems, again, which are just meant as exercises. Problem number 6a asks us how much is 453 times 49 plus 453 times 51. Now remember, everything inside parentheses is treated as one number. So the first number inside the parentheses is 453 times 49, and I will leave the details to you now because I've multiplied enough of these out for you. Verify that these multiplications are correct. If I multiply 453 times 49, you see I am going to wind up with 22,197. By the way, I've never mentioned this to you before, but if you're watching this on your own, nothing prevents you from pressing the pause button if you want to verify something and I'm moving too fast for you, stop the tape, do the computation, and verify that what I did was correct. At any rate, the first parenthesis is 22,197. The second set of parentheses is 453 times 51, and if I multiply that out, I wind up with 23,100. 23,100. Now, what am I supposed to do next? I'm supposed to add these two numbers together. I suppose it's easier to do in vertical form, you see, and if I add these all together, I get 0, 0, 3, 6, 5. This is not my day. That's okay. 5, 4. Okay? 45,300. And that's the answer to part A. By the way, you may have noticed that 45,300 looks an awful lot like 453. And it should, because look what this says. I've taken 49 of these and 51 more of these. Isn't 49 plus 51 100? And how much is 100 453s? It's 453 with two zeros annexed, and that's where the 45,300 comes from. And that's precisely what part B was asking us to do over here. I'm just going to jump over to part B over here. I do have something on the top of the board that I'll come to in a moment. It's sort of a digression, and as I'm going through the lecture, it occurred to me that maybe I should mention it later. Let me just say for the time being that all you're doing in part B is you're showing that you're writing this, and notice that by a distributive property, how would you write this out? It would be 453 times 49 plus 453 times 51. That's part A of the problem, but also notice that 49 plus 51 is 100, and that's where you would get the 45,300 from. By the way, notice the use of the grouping symbols over here. The use of the grouping symbols say what? First add the 51 to the 49, and then multiply. I want you to see that the grouping symbols are important. So part C was done simply to show you what happens if I switch the grouping symbols. You see what I did now? By putting the grouping symbols this way, this says first multiply the 453 times 49. See, do everything in parentheses first. Then you add the 51. See, so this would say what? 453 times 49, which we already found out to be 22,197. Then we add the 51. That gives us 22,248. You see, there's a big difference between this answer and this answer. And the only other thing I wanted to show you, I'm going to go to the top of this board now. I should have really put this in as a digression. In fact, I guess I started to do it this way and didn't finish the parentheses. You see, a quick way to multiply by 50. Since 50 is 100 divided by 2, I want to show you a number sense again. What I could have done to multiply by 50 is tack on two zeros. You see that multiplies by 100. Then divide by 2, and that would give me 22,650. See, 54 53s would be 22,650. So to find 49 453s, I would just subtract one of the 453s from the 50 to give me my 22,197. And to find the sum of 51 453s, I would have taken 50 453s, added one more 453 onto it, and notice that this gives me an alternative way of finding the same answer to the problem. Now what I want to do is turn our attention to the division process. Okay? Let's do some of the division problems. Problem number 7 says, how much is 34,722 divided by 643? And as a multiplication problem, what it really says is, what must you multiply by 643 to get 34,722? Well, you see, remember how we do this problem? You look at the 643, you look for the first number that's bigger than 643. See, 3 is smaller, 34 is smaller, 347 is smaller, 3,472 is bigger. How many times does 643 go into 3,472? Well, we'll take a guess, around 5 times. See, so now I multiply by 5. That's 15. 1 carry the 2, 32. So I put the 3215 down here. I subtract, that's 7, 5, 2. I bring down the next digit, which is a 2. Now I take another guess. How many times does 643 go into 2572? Well, 6 goes into 25 about 4 times. I'll try that guess. See, and if I put a 4 here, see, 4 times 3 is 12, carry the 1. 4 times 4 is 16 and 1 is 17. 4 times 6 is 24 and 1 is 25. This goes in exactly the right number of times. There is no remainder. So the answer to part A is 54. By the way, if you say to me, how did you know there's supposed to be a 5 here? Let me remind you of something we did before. Suppose you took a guess and thought it only went 4 times. 643 times 4 is 2,572. And if you subtract 2,572 from 3,472, the answer is 900. And why do I know that that's wrong? Because 900 is bigger than 643. I can still take out what? One more 643 from this. And now if I subtract, I get what? 752, which is the same thing I had over here. You see, if you ever guess wrong, one of 2 things will happen. You'll be subtracting too much, which tells you you picked too big a number, or you'll be subtracting too little, which will, or you'll have more left over than your divisor, which will tell you you've subtracted too little. Okay, do you see the idea there? Now, problem number B, part B, is just a rewording of part A. Part B says, what number must you multiply by 643 to get 34,722 as the product? Well, you see, in problem A, we showed that 643 goes into 34,722 54 times. And what that means is, if you were to multiply 643 by 54, and I will leave the details to you, see what should happen here? If you multiply this out, what should you get for the answer? 34,722. See, we've already done this problem before, all right? And now what we now know is that therefore the number you must multiply by 643 to get 34,722 is just 54. And part C is just the rewording of A and B. You see, what I want you to see is that when you do either A, B, or C, you've done all 3. See, part C says, is 34,722 a multiple of 643? See, what that says is, if you were counting by 643s, would you ever come to 34,722 exactly? And the answer is yes. Not only is the answer yes, but 34,722 is the 54th multiple of 643. And you know I'd never give you a homework problem within a homework problem. I've worked this out for you over here. So disregard the homework problem I told you to do. There's this whole thing worked out. Just make sure you understand how A, B, and C are related. And problem number 8 is almost the same thing, but with a few more wrinkles here that I'd like you to see. See, problem 8A says, what is the quotient when 204,624 is divided by 504? In other words, what that really says is, if you were counting by 504s, would you come to 204,624? And if so, when? So all we do is, again, the number we divide by, that's called the divisor. That goes outside. That's the goes into number. See, 504 goes into 204,624. And now what we do is, see, we look for the first number that's bigger than 504. See, 2 is too small, 20 is too small, 204 is too small, 2,046, that's bigger. 5 goes into 24 times. We'll take a shot at it. We'll try 4 over here. 4 times 4 is 16. 4 times 5 is 20. This comes out to be 2,016. Now we subtract. That gives me 30. Now I bring down the 2. Does 504 go into 302? No, 302 is too small. But remember, anytime something comes down, something else has to come up. So since there are none over here, we have to put a 0 in. Now we bring down the next number, which is a 4. 5 goes into 36 times. We'll take a shot at it. See? 24, 30. Worked out fine. So the quotient is what? 406. In other words, when you're counting by 504s, 204,624 is the 406th number you would come to. And again, as a check, what should happen? If you multiply 406 by 504, you should get 204,624. Again, it is crucial that you do not omit this 0. Because if you leave the 0 out and put the 6 in, what does that make the 4? It makes the 4 4 tens, and the answer is 46. Now you see, take a look over here. 504 times 46. Well look, 504 is less than 600. 46 is less than 50. 600 times 50 is 30,000, and that's too big to be the right answer here. That's way less than 204,624, so this must be the wrong answer. Now I want to illustrate to you that sometimes a given number won't be a multiple of another number, and when that happens, there will be what we call a remainder. And that's what problem 8b asks us. It says, what is the remainder when 205,000 is divided by 504? This is the same type of a problem as part A, only now the 504 is going to be divided into 205,000. Okay? And basically the idea is this. We still start the same way as before. 5 goes into 24 times. See, this gives us the same 2016. We subtract 2016 from 2050. We get 34. We bring down the 0. Now be careful, 340 is still less than 504, so we have to put a 0 here. Now we bring down the next digit. Okay, that's a 0. 504 goes into 3,400 6 times. 6 times 4 is 24. 6 times 5 is 30. When we get all through over here, we have 376. That's less than 504. Okay? That's less than 504. There are no more digits to bring down. And by the way, what that means in terms of a practical problem is if you had 205,000 books to pack, and you could put 504 into a carton, when you get all through counting them, putting them into cartons, you would have 406 complete cartons and 376 of the 504 you would need to fill the next carton. See, that's called the remainder. And by the way, there's an easy way to see this. You see, basically what's happening over here is that we saw that 204,624 was the 406th multiple of 504. The next multiple would be what? 504 more than this. If I add 504 onto 204,624, I get 205,128. So you see, notice that 205,000 is between what? The 406th multiple of 504 and the 407th multiple of 504. And that brings us to the answer to part C. Namely, it says, is 205,000 a multiple of 504? And the answer is no, because when we count by 504s, the 406th multiple was too small to be the right answer, the 407th multiple was too big, and there are no multiples of 504 between the 406th and the 407th. Problem number 9 is again a long division problem, and all we want to show you there is that the technique works exactly the same no matter how many digits are given. You see, this says find the quotient. We're dividing 7,543 into 17,356,443. I like to leave the commas out because the commas confuse me sometimes. So basically what I do is I look to see the first number that's bigger than 7,543. That's where the 6 is. You see, that's 17,356. So I take a guess. I try 2. 2 times 7,543 is 15,086. I subtract 15,086 from 17,356. That gives me 2,270. Then I bring down the 4. I see that when I bring down the 4, I guess that 7,543 goes into 22,704 3 times. So I multiply by 3. 9, 2 carry the 1. Okay, 6 carry the 1, 22. I subtract the 22,629 from this number here. I bring down the next digit, which is a 4. And this is the tricky part again. You see, I've brought down a digit. That means something has to go up here. But since 754 is less than 7,543, I have to put the 0 here. Now I bring down the next digit. 7,543 goes into 7,543 one time. And so the answer is what? 2,301. In other words, if you're counting by 7,543s, 17,205,000 356,443 is the 2,301st number you'd come to. And you say, my God, who cares about that? Well, the point I'm trying to show you is that if you ever had to do that kind of a problem, imagine trying to do that by tally marks, by addition. Look how wonderful this process of division really is. At any rate, we're kind of winding down, so let's get on with the last problem. And the last problem is designed to show you that just as addition and multiplication are associative, but subtraction isn't, neither is division. See, what I'm going to do in problem number 10, in part A and B, I'm going to do essentially the same problem twice, except that the parentheses are going to be shifted. See, remember, everything inside the parentheses is done first. So part A says, take 138,720 and divide that by 24. So that's what I do over here. This is just, again, for you to check out. See, 24 goes into 138 5 times. 5 times 24 is 120. I subtract, I get 18. I bring down the 7. 24 goes into 187 7 times. 7 times 24 is 168. I subtract 168 from 187. I get 19. I bring down the 2. 24 goes into 192 8 times. Okay, I brought down the 2. 192 from 192 is 0. And this is tricky. There's still a 0 over here. I have to bring it down. 24 goes into 0 0 times. That 0 has to come up here. So this is another name for 5,780. And now what do I do next? I take the 5,780 and I divide that by 4. 4 goes into 5 once with a remainder of 1. 4 goes into 17 4 times with a remainder of 1. 4 goes into 18 4 times, the remainder of 2. 4 goes into 25 times. The answer is 1,445. Part B looks exactly the same as Part A, except that the parentheses were shifted. Can you see that okay? See, look at Part A and look at Part B, and notice that if I erase the parentheses, both of them read 138,720 divided by 24 divided by 4. But this time, you see, what's inside the parentheses is 24 divided by 4. That has to be done first. That, of course, is 6. So this becomes what? 138,720 divided by 6. The 6 is the outside number in the long division form. 6 goes into 13 twice with a remainder of 1. 6 goes into 18 3 times with no remainder. 6 goes into 7 once with a remainder of 1. 6 goes into 12 twice with no remainder. 6 goes into 0 0 times. In other words, now the answer is no longer 1,445. It's 23,120. Because you see, by dividing the 24 by the 4, the final division is being done by a smaller number. You see, here's the thing I'm trying to point out to you. A and B may look alike, but those parentheses, that voice inflection, makes a big difference. And for our finale today, look at Part C. Part C looks less like Part A than Part B does. You see, Part B had a division sign over here. What we're going to do over here is observe now that we're multiplying. This doesn't look like a division problem. This doesn't look at all like problem number A, does it? See, Part A said first divide 138,720 by 24. Remember how that looked? It was this. And then you were going to divide that answer by 4. This says what? First multiply the 4 by the 24. Well, that's 96. That was the first problem we did today. This says take 138,720 and divide by 96. If I divide 96 into 138,720, look what I get. I get the same answer I got in Part A. And the thing I wanted to show you is that if you divide by a number and then divide by another number, it's the same as dividing by the product of the two numbers. I just wanted you to see that before we quit. See, here's a rectangle. If I divide it by 4, you see I break the thing up into 4 parts. Now if I divide that in turn by 2, each of the 4 pieces becomes 2 pieces. So altogether, how many equal parts did I divide this into? 4 times 2, or 8 parts. I'm not asking that you master all of this. All I'm asking is that A, learn how to do these, and B, as fast as possible, try to develop a number sense so that when later we get to word problems, you'll understand better how to do them. In any event, this wraps it up for now. Next time when we get together, we're going to introduce the study of what's called rational numbers or fractions. Until that time, have fun, stay young, learn a lot. I'll see you again soon.